So in today's session, will be on the MATLAB for the engineers. So since I'm from the electrical engineering background, so I'm much more familiar with the uh, Simulink toolbox and especially on Simscape and power systems. And I can throw you in light over that how we can use MATLAB. Right? And on the left side of this of my screen, I have the current folder, which shows the current working folder and the files contained in that particular folder. On my right, I have the workspace. Workspace is the space provided in this MATLAB where the active data or the results or the inputs are stored here in the workspace. Let us say uh, whatever the data I create here in the command window, or whatever I execute via the file, the variables will be generated in the workspace, either as an input or output, whatever the data here, that will be stored in the workspace. And from the workspace, we can perform any sort of data operation. So essentially, for handling any data, your MATLAB immediately it will look into the workspace. Either you are going by code or we want to execute some GUI files, that is your Simulink files. The data will be taken from the workspace and will be stored in the workspace. So let us create a very simple, just I'm creating a variable. Let us say a equal to 0. So it stores an a as an array, which comprises of an one row and one column of data. So if I double click on this, I'll get a new window with the file seems to be like in an Excel format. Yeah, similar to that Excel format. I can have this, right? I can close this. So now if I want to modify the data, I can modify the data over here. A is 5, 2, then 3. I'm just giving a random data, right? If I close this, so it shows A as an array over here. Now if I type A, immediately whatever the data present in my workspace will be delivered now. You can see initially I initiated A as an A equal to 0. Now then from the workspace I modified the values of A, and then I typed the command A, so it outputs the information whatever the data that is stored. So I have an A is an 2 cross 2 array, right? Similarly here itself I can read as suppose if you want to modify, I can do this data here. I did not, right? Now it's an 2 cross 4 data. If we type A, it throws information like this. Suppose if you want to modify this, the data, I can have like within the square bracket, I can mention, and the elements are separated by space. 1 space, 2 space, 3 space, 4. Right? If I do this, I am generating a row vector of 1, 2, 3, 4. Or suppose if you want to generate a column vector, then what I need to do is 1 semicolon. So in between the data, I need to introduce a semicolon. If I do this, I have generated a column vector. This how basically your MATLAB handles the data. Suppose if I don't want to display my variable each and every time I type, just I should terminate the line with the semicolon. Then the corresponding value will not be displayed in the command window. Then I can use the CLC command. It will clear the command window upon execution. If I use clear all, then whatever the data that's stored in the workspace will be cleared, right? So usually what we do is whenever we try to write a program, we'll use these two commands, CLC and clear all. Means to clear all the workspace variable, and then I want to have a clear command window like this, I can use it, right? And so these are the files which are already stored in this. And there's some defaults folder. I have it. Now, if you look at the home, you have the option to generate a new script, new live script. Then you have the new option. When I click on that script function, live function, I can go create a figure or state flow chart or Simulink model. So this is a generalized option to click to select what are the function we want to generate, and this open to open the already saved files. You can find the files and you can compare using the compare operation. If you want to import data from the file, I can click on this. If you have an Excel data, I can import it by clicking on this. With the recognized data file, I can have it. Then clean data. Whatever the data I store here, I can erase it. Sorry. So here I can analyze the code, and this is the Simulink, which is going to be a graphical user interface platform. This is the start of this. So I can create a small program by clicking on the new script. So I can start clear all, then CLC. These are general declarations what we give to clear off the workspace and all. And then let me again I'm creating a variable, right? I'm just terminating this with a semicolon, because if I don't use this semicolon, then it will ask for it will keep on displaying the data. I can tell you that. So I can perform like in normal programming languages. C is equal to A plus B. If I want to display the result, I need not to type this. And we need to we need to save this file. We need to save this file. Then if you execute, it generates an output. It adds the data one by one. Or else here, what I can suppose if I terminate this with a semicolon, then we can observe the result is not displayed, but the data is stored in your workspace, right? So if I want to see the data over here, I can type this, and if I click on the variable, I can go for another option in the menu called your plot. So depending on the type of data storage I use here, I can select different types of plot that are available here, right? So let us say I'm using a command plot. It plots that information. So if I want to plot this as a discrete data, I can use the command stem. So it shows 3, 5, 7, 9 at the different instances. Or I can use this step. Right, like this, we can, whatever the way we want to visualize the data. The recent versions are supporting the information in that pattern, right? I can have this scatter plot, or else I can have this pie chart. It indicates the percentage, and whatever the data I modify here, accordingly it will be reflected in this, right? Suppose if I use a transfer function, then I can find the control parameters over here. Let us see. Let me define a system. S is equal to TF. TF is a command which indicates the further for the argument passed within this bracket indicates a transfer function, right? Here again, if it is a transfer function, I'm just going to give it only the coefficients of my numerator and the denominator polynomials. So let us consider my transfer function is 1 by 1 plus s. So how I'm going to give this is 1. This is going to be the that is TF of numerator comma denominator. This is the template for this. So 1 comma within the square bracket, I'm going to give 1 space 1, where here the first one indicates the coefficient of S and the second one indicates the constant coefficient. So here how the coefficients must be entered is, we should start from the higher degree, the coefficient of higher degree to the constant coefficient. If I do so, it shows in continuous time transfer function, S is equal to 1 divided by S plus 1. And you can see the corresponding transfer function is stored like an variable and the icon like this. Now when I click on this, I'll get the plot options that are corresponding to the system analysis, the time domain analysis of the. I can take the board plot directly. See, it shows that the frequency response of the system, right? And now if I click on this one, I can get the characteristics. I can find out what is the peak response, and I can find what is the minimum stability margin, and I can find all stability margins for the system, right? This I can perform this. Okay, so this is one way I can use my MATLAB here. I can take this root locus. So since it's a single pole system, it will find it 0 at infinity. I can perform the stability analysis also from here. Right. And if I right click on the go to the properties, I can modify my the that is my x-axis label and y-axis label and plot name. I can define the limits for my scale, and I can use the units. In what style I can have this plot. Okay. So like this, we can explore the various functionalities of utilize the functionalities of the MATLAB, right? And whether if you want to for the same system, if I want to generate multiple plots, then I can click here whether I need to plot it on the same figure or I can go for a new figure. If I click on this new figure, okay, so whatever the plot I keep here, it will generate different plots. So I can have this figure 3 step response plot. So I can see I have figure 1, figure 2, figure 4, and figure 3 like this. This option is available only if I click on this new figure. Suppose if I give reuse figure, it will take that last used function field, or with whatever is the active window, it will plot on this. Right. So the figure 2, it has now been written by this. Okay, so these are the shortcuts we can use for the analysis. And here we have the app. In this apps, we can what to say, whatever that is functions we want to perform, or if you want to install new package, if you want to install any apps which is going to be compatible with the MATLAB, we can perform this. So let us say, let me see the PID tuner block. Okay. So now, since this is a transfer function, for this transfer function, let me design an PID controller. Right. So First of all, what I need to do is I need to import my plant into the tuner. So I can take the plant, I can import it from my the workspace. So this is my plant which I have taken, right? And this is the step response, unit step response of my plant. Now, what is the type of controller I'm going to use? Whether I need a proportional controller or integral controller or PI or PID or any sort of control I'm going to have it. So with 1 degree of freedom, 2 degree of freedom. Let me start with my PI controller as in simple. And you see this, this is the a tuned version of the controller. My KP value is 1.042 and KI is 3.128. This was automatically tuned upon selection. And again, I can choose in what domain I need to select my uh, design my controller. Either I need to go for a time domain approach or in the frequency domain approach. So in terms of frequency domain approach, the control parameters, if you see this, I'll consider the phase margin and then the bandwidth. If it is a time response, I'm going to see slower or aggressive. In what way I'm going to have it, right? If I can adjust this. You can see how the parameter modifies. Suppose I want to have a faster settling. Initially, it was around some 4 or 5 seconds. You can see this. If I move this slower, it goes up to 1200 seconds. I want to have a faster response. Right. So now the system settles in 5 seconds. Now I can want to have it a bit more faster. I can increase this. Now we can see if you observe this time axis, initially it was settling at 5 seconds, but here now as we speed up, it is settling at the time period less than 5 seconds. Say here it is 2 seconds. But one thing what we need to understand here is if I reduce my settling time, it reflects in a way that the peak overshoot is increasing. Suppose if I want to work on this peak overshoot, I don't want to have this much of peak overshoot. I can go for this, right? So I have greatly reduced my peak overshoot. Now I can adjust it again, right? So whenever I attain my satisfying response of the system, then I can import the controller. So here if you want to view the parameters, it shows here. This is my value of Kp and this is the value of Ki, that is the gain of proportional control and integral control. And you have this time response parameters like rise time, settling time, overshoot, the peak and gain margin and phase margin. And there is a comment on the closed loop stability. So the system is stable. So once these parameters are met according to the desired specification, then we can say that the controller tuning is done and I can import this into my workspace. So I can use this as an export option. While exporting, I can export either as in a controller for this plant, So if you see this, I have the controller C implemented here as a transfer function, right? Now it has whatever the parameters we defined over there. We have it. This PID tuning. See, this is one of the graphical user interface which simplifies our design procedure. Right? Any clarifications up to this? Fine. So now I can what to say, right? This is about the live script. So what is the difference in this live script is parallelly we can verify the output here. Whatever the things we code here, let us say 1 space 2 space 3 space 4. So this is an live editor where parallelly we can view the outputs on the side. As we keep on moving, we need not have a separate execution cycle, or we need not have a separate what to say that whatever the commands we execute here, everything will appear in this. So this is about the live editor. So whatever the active data that are present in the workspace, everything will appear here as you keep on coding it, right? Nothing much difference between this live script and then regular script. Just only thing is here, whatever the data that are available in this, that can be directly imported and it can be processed in this editor file. Okay, and then just this one. This is one sample code, like how the data is being processed, right? It shows here, and can see here you have an ampersand. Sorry, the percentage symbol for is after whatever comes after the percentage symbol in the same line will be considered as an comment. Okay, so a double percentage symbol indicates it's an new section, right? So this is the brief, a very brief about introduction about the MATLAB command windows, MATLAB command section or MATLAB script. Then we'll move on to the Simulink, which is a graphical user interface. So when I click on the Simulink, it will ask for creating a blank model or a blank subsystem, blank library project or folder like this. Or else I can directly use and from this also. And a particular just a basic filter or in a DSP system. When it click on the embedded coder, it will ask for some embedded applications, right? Like this. Or else I can start with a basic, a blank model where I can define upon whatever I need. I start with a blank model, right? And this is the library browser. So in this Simulink library only, the definitions of whatever the blocks we are going to use in our system are going to be defined and it is stored. And we are directly going to and it's directly going to reflect. We can directly use it, right? And you can see here Simulink. If you click on this triangle, it will expand, means it will show its subfolders. And again, if you click on this, it will show either the subfolders or the components, whatever contain that particular folder. Like this, if you see the toolboxes, Simulink, which is a general toolbox, which is used in all other libraries, right? So basically, if you see this, this Simulink folder or the browser will comprise of commonly used blocks, mathematical operations, signal routing operations, and then scope, etc., etc., etc. here. And then you have that automated driving toolbox, computer vision, control system, deep learning, DSP tool with a HDL support, embedded coder, and then embedded coder and embedded coder support package for Texas type of instrument, Texas processors, and fixed point designer, HDL design, fuzzy logic toolbox, HDL coder verifier, instrument control, mixed signal, motor control with the HDL support. So the nowadays MATLAB comes with a variety of feature from means from MATLAB platform itself. We can generate the programming codes required for an embedded coder or an VHDL controller or FPGA controller, or I can directly use it with for generating the code for an OpenRT control. Like this, I can generate the codes, or I can directly program an DSP processor right from the MATLAB. But only MATLAB alone is not sufficient in such cases for generating the code. What I need in addition is I need to have the uh, hardware support software packages for the respective controllers. Then only it is possible. For an example, if you want to interface the Texas systems, Texas microcontrollers, I need to have a Code Composer Studio. I need to have a Code Composer Studio platform, which is going to integrate my processor with my MATLAB logic. Okay. So likewise, I have so many block sets here defined here. Now let us see basically how I can use this MATLAB for data generation or mathematical operations that I can perform here. So let me just I try and simple system to implement here. I'll use an a transfer function integrated. Yeah. So just drag and drop. Whatever the element I need here, I need to click on this, drag and drop into the file. Or else if I right click on this, add to the it will ask for the file name, whether it is stored. If I already saved it, it will show that file name. Since it is not showed, it shows as an untitled, right? So let just whatever the transfer function I used here in the script, the same. Let me use it here. Now in this transfer function, I need to find the step response. So the inputs are available to be taken from the source. I need an step input source. So the step input is available. Just dragging it here and I'm connecting. I want to see the output of this by using an scope. So scope, I can take it from the sink. Sink means where I want to display the data. Where I want to store the data is going to be the sink. It's not store or where I want to view the data. It's going to be a sink. Now for this, let me configure the input. Find the step time. Let me keep it as 0.5. Initial value is 0 and final value is 1. Means from 0 to 0.5, the initial value will be 0. From 0.5 to 1, the step source will generate an output of 1. Apply, click on the transfer function. I'm not modifying. And here the data, the scope I'm connecting. Let me run this for the duration of 2 seconds. When I double click on this, sorry, let me repeat this once again. So here let me simulate a very simple system, first order system, whatever I taken here. From the continuous blocks, I'm taking the transfer function, right? And from the to this transfer function, I should apply some input. That input signal, I'm taking it from the source block. Source is the one where you can get the signals. You can have so many different types of signals. In that, I'm taking an step input. So step input, the block, I'm keeping it and connecting. I want to see the results or the output of this simulation. So I'm taking a scope from the sink. So I'm connecting the scope and I'm configuring the input. Step time, let me give it as 0.5. Initial value is 0, final value is 1. I'm not modifying anything. And then scope is connected. And let me run this for some 5 seconds. Right? When I click on the run, it is getting executed. And you can see this. This is the response. Right? At time 0.5, I'm applying the input. The input is swapping from 0 to 1, but if you see that system output, it is not. And again, if you see this, I can modify this. I can customize this by clicking on view style. I can change the figure color and axis colors to white. and black. I'm making it ulta. I can change the thickness of the line here, and I can change my line color also. Once I give apply, it's been modified, right? Okay. And then I can change the layout and the number of inputs I can have it, right? So when I click on the settings, number of input port, let me take it as 2, and I apply OK. You can see it is now been modified to 2 inputs. So to the first input port, I'm connecting the input signal, and to the second port, I'm connecting the output of the system, right? When I run it, the first input, and this is my second input. I can change the style, active display, the step output. Here, I can modify this. So the one in the red is the input, and the one in the blue is the output of the system, right? Like this, I have the provision to modify or customize my system, right? Now, if you want to design an system, a closed loop system, closed loop control. Earlier, we had designed the PID control, right? I can use this controller over here. Just let me check. Yeah, I have this controller here. C, right? I can take this function. Okay. Or else I can directly now I can use in PID controller. And there is another way to to bring the blocks. If you are well aware about the name of the block, just click on the white space, then you start typing. It will show, it will suggest you the list of terms and blocks that are available in the search terminology. So PID controller, I need, so I typed this PID. Now I can double click on this. Whatever the way I want to implement, I need an PI controller. Whatever the parameters we taken earlier, I am going to have it. P indicates KP, I indicates your KI. So the values of the controller parameters, I'm going to take it from this tuned parameter. So 9.1807 is my KP. And KI is 18.773. Right? I'm applying this. Okay. Now this controller should be in between the plant and my input. So let me remove this. If you place on the wire, then automatically it will get adapted into it. And I want to take the feedback, right? I should now for that, let me have this sum block. So this is my reference input, and this output I am sharing as in feedback. So this error I'm feeding as an input to my controller. And before that, what I need to do is I should have the sign change from plus minus. Reference minus actual output, and it will provide you your system response. Right? I'm running this. You can see the performance what we had similar to that of the controller. We achieved it. We achieved it here, right? First, what we use is an PID tuner app. From the PID tuner app, for the given transfer function, we derived the control parameters, and those control parameters we are implementing here, and we can use it for our application. Any clarifications do you seek here up to this? Okay. So basically, if you see this, as of now, any clarifications you have with respect to this Simulink? So the point, one question has been asked, how we can use MATLAB for the data science application. So basically, MATLAB is an mathematics tool where we can compute whatever your data science operations. Data science is basically what is that? How we are filtering the data, how we are considering the samples, and how we are calculating the average, mean, median, standard deviation, and then variance of the function. All these things we can calculate, we can determine by using your character user interface. You have standard functions like how we use the C programming. Likewise, we can import the data, we can process it, we can compute it, we can filter it, or whatever the mathematical operations or whatever the statistics we want to perform. All those statistics we can perform using either your live editor, or from that we can run the information. And whatever the data that are available in the CSV format, comma separated values format, you can import those data into the workspace. You can use the tools, the statistical tools that are available here, right? And again, those statistics tools, for that also I need to look into the browser, that my library, right? And whatever I installed is a limited version of the libraries, considering this space and my application requirement. I used an minimal package only here, right? So in this one, you have statistics toolbox also, which actually I did not prefer because that particular application is beyond my scope. And the next question, what I addressed, what I noticed here is some how to install MATLAB. actually installing MATLAB. For that, you need to have an license obtained from the MATLAB. You can log in. You can create an account of yourself by yourself from the MathWorks site, or else if your institution has an subscription for that, you can use that version. And once you enter into the MathWorks site, you can download whatever the version you want. So here I just yeah, I'll show you in this site. Now if I click on this MathWork, already I have my account. So now if I click on this, I can check right in my account. I can whatever the software I install, I can have it here. Or else I can, if you want to have an additional license, I can click a link to it. Or if you want to download my new version, I can go for it. Right? You can see my MATLAB. I can go these are all some already I've used some programs here. I can click on install MATLAB. Once I click on that, then it will ask for what type of what version I need to go for it. And MATLAB, if you see that, these are all the versions available. This is the earlier one, and every year if you take that, MATLAB will have two release, A and B. For every 6 months, they will MATLAB will release one new version, right, with some more packages. Okay. So currently it is 2023A is the recent package, and for the already existing users, they are providing an pre-release 2023B. This is now only the preview is going on for 2023B, and this is the way we can we can install the MATLAB. And once if you install this further, if you want to add some more packages, in that case I can uh, use this option. I can click on the add-ons option available here. In this I can get add-ons, I can manage, I can download the package toolbox and hardware support packages and all. Once I click get add-ons, then it will take me to the new page, the add-on explorer. Right, so now here I can filter it by the source or the type of products, uh, whatever is available here I can take it. Device driver, you can scroll down and you can see this, whatever is the tool you needed. If you have a valid license, then you can download that particular toolbox. Right, this how you can see this. For Arduino also you have the MATLAB support package. Whatever the logic we want to realize, that can be done, and that directly we can transfer that into the code. So this is possible by the MATLAB. Any more questions on this basics? Yes, online MATLAB is also available, but further also you need to have an account. So, uh, I'll move on to the next thing. Just and I'll take a simple electrical engineering application where you can a simple power electronic system. Let me implement. I'm creating a new model. What I do here is I just have a simple control of a switch, right? I'm going to have an battery. For that, I'll go to the browser, then Simscape, electrical. I'll go with the specialized power system. You see this much folders are there. I'm using it. And here I want to use my sources. In my source, I have a, let me take a battery or a DC voltage source, right? And then I need an switch. So I take an MOSFET or an IGBT switch. Then I'm going to have a load. So load I can take it from passives, series RLC branch. And for the purpose of measurements, let me take here from sensors and measurement. I want to take the current measurement and an voltage measurement. Right? And then for power electronics or any electrical applications, I need this power GUI, means power graphical user interface. Only if this particular block is present, then only whatever the components I take it from this specialized power system will work. Okay, so this acts like an yeah, map between my whatever the blocks I use here and its corresponding definitions which is stored in the library, right? Because there are cases where you have multiple elements are present under the same name, right? And in order to view this current and voltage, I'm using the scope. Let me copy this scope from here because I configured some changes in this. So what I basically do is I'm going to connect my these three elements in series: source, a switch, and a load. Now I want to measure the load voltage. So I'm connecting the voltage measurement block across the load, and current I can measure in series only now. So I have to actually break this, right? This is my current measurement block. Okay, and let me change this load to a simple resistive load of 100 ohms, and let me consider this battery to be 24 volt. And this switch is an electronic switch which must be operated electronically. So I should use an PWM source. So I need an pulse. So I go with an pulse generator connected to the gate terminal of your switch. And this M indicates the measurement port. M indicates the measurement port, which I can have it or I need not have it, right? And yeah, current and voltage, the measurement ports are connected. Okay, and whatever is required, I just made it. And in this, it was mentioned as continuous. What is that? Now, MATLAB, how it is going to process whatever the blocks we are or the codes we are introducing, it's going to convert into an equivalent differential equation and it is going to solve it. Right. So while performing that continuous, while solving those differential equations, how the differential equations are considered. If you are mentioning to be a continuous time system, then it will calculate output as an continuous term with a continuous domain, so called the differentiation, which usually will drag much more time. So what we can do is we can convert this continuous to discrete. And discrete, it will ask for the sample time. By default, it will be 50 microsecond. So what is the difference between your continuous and the discrete mode of operation is? In continuous mode of simulation, the equations are solved and the solutions are updated for every microseconds, nanoseconds duration. But whereas in the case of the discrete solving, it happens only at the discrete instance. For an example, here we have set that discrete time or the sample time to be 50 microsecond. So at time t equal to 0, one computation will happen. And at time t equal to 50 microsecond, the second solution will be taken. In between 0 and 50, there won't be any 50 microseconds, there won't be any solutions. Okay. And then the next computation will happen only at 100 microsecond. Whereas in case of the continuous time analysis, in between 0 and 50 microseconds, I will have so much number of computation which unnecessarily delay the system speed. That is the speed of computation and all. So for that reason only, we especially with respect to the power electronic systems, where it forms a discrete structure, we go with the discrete types of simulation. Now I can run this for 1 second or even less. The pulse generator I need to configure, right? The amplitude of pulse is the peak to peak 0 and 1. Period. One complete cycle is referred to the period of your pulse. Let me have this as an 1 kilohertz, 10 kilohertz. So time period is 1 divided by 10,000. And let me take this 50% as the duty ratio. I'll tell you this how the pulse will look like. Let me have this number of ports to be 3. Right. And this is my layout. 3 cross 3, I just modified. I have connected the pulse. Okay. Okay. I'll take it in this order. Input voltage, the gate pulse, output voltage, and the current. I'm running this. Yes. We can see this. This one is the gate pulse, whatever we provided, and we can zoom in and zoom out. The option is there. This is for X zoom, this is for Y zoom, zoom out, and I can pan it. You can see this. Right? And so here, let me the pulse generator to display 3, the current measurement. Let me So whenever a load voltage is present, then only the load current flows here. And again, if we see understand here is instead of providing an 24-volt constant. Now it has an 50. If I want to correlate this with my, yeah, you can see this duration will be like 1 by 10,000, right? It was 0.0001. Now if you measure this 0.1221 and 0.1222, the difference between both is 0.0001. So this corresponding to frequency of 10 kilohertz. And among this one cycle time period, the pulse width of 50% means the pulse is on for 50% and it is going to be on for 50% of the time. So in that in this time period, 50% is an on time, the 50% is the off time. Okay, so this is what the degree, this is what the values we are providing here, and these are the phase delay. This phase delay will come into picture or effective only if we have more than one pulse, then only we can understand it. So this is one simple application what I consider with respect to the electrical, right? And here I can use the neural network tool by using the command nf tool. We use this nf tool, it opens an curve fitting toolbox, right? So this is the neural network model. Input, hidden layer, your output layer, and this is going to be the final output. Now how to train this? So for training this, before that we need to have to import the data set into the workspace. So use the import data, means whatever the data we have already that can be taken into the workspace from the current active folder, or else I can take the already example data. So I'm taking an import body, just an example data I'm taking. And here I need to specify how many layers I should have at the input and the output, and what is the size of the input. All those things I'm specifying here. You see this, the input has the data size of 13 and it has 10 hidden layers and the one output layer generating and one output. Now I can modify this layer size. See, if I increase this, if more the number of layers means more number of variables are present. So depending on the number of variables or the process we are going to consider, we can increase the number of layers here. And we are specifying what is the value for validation, how many data we need to use it, and for testing how many data we have to use it, right? Accordingly we can fix it here. Once this is done, then we have to click on train. Okay, so here I can select what type of algorithm I can use. So by basically you have an Liebenberg Marquardt algorithm. So it is training. Finally, it has met the validation criteria. Once it is done, it will throw you the data. So it will show you how much epochs it has been taken and what is the time elapsed. And for this particular system, it doesn't take much time. It has converged very fast and with the desired specification. And finally, if you take this, it has attained the target value in the 12 iterations. Just in 12 iterations, it has completed. And you can see this, how the performance is validated based on the mean square error. So these are the data operation, mean square error, and this is the regression value. That is so-called your correlation, right? The correlation inputs based on the correlation parameter, we can find it. Suppose if you want to perform this, take the in-between value, the training state. All these will give the information in terms of plot. You can see in the 12th iteration itself, we attained the best value, right? And this is about your performance plot. It shows the convergence, right? And error histogram. If you are very good at dealing with these numbers and the mathematics, you can go for it. And this is the regression, which shows the closeness of your training data with the test one in all the states. Once this is done, I can have it like either I can generate the code or I can generate the model. So you see this, either I have the option to export the neural network into the workspace or as a separate Simulink block, right? You have a separate Simulink block, it's been generated. So this is your generated neural network. And we can give the inputs here and we can measure the outputs here, right? In electrical application, we consider this while feeding the data here at the input end. We provide, so normally in our process, what we have is we'll use this neural network as a controller. So when the controller means, I should consider what is my reference value, what is my actual value, and error. Based on the error, I'll modify my control input. So accordingly, I can check in what direction I have to move, either in the positive direction or the negative direction. So I'll consider two inputs. One is error, and the other one is the rate of change of error. Either for my given control input, whether the error is increasing or decreasing. Accordingly, I have to modify my input. Means I have to take my control action accordingly, right? This in this way we implemented. So for that we need two training data. One is error, the other one is changing error. Change in error. That is d by dt of the error. We'll take it. So those two I'll provide as an input data required for the training, and then I'll generate an output. So this how we process the neural network toolbox for our engineering applications. That is for the electrical engineering applications, and this can be used for any sort of thing like your data interpolation or extrapolation. Also, we can use this neural network, or we can use another tool called support vector machine, which is in short it is referred to SVM in the machine learning techniques, right? And this data science and machine learning has been emerged in your field because of due to the development in the computation domain. Since you have what to say, much sophisticated computing facilities like unlimited memory, high speed processors. This particular domain called the data science and machine learning got an boom again in this particular domain in this current era. Earlier it was there, but the drawback what we had earlier is your costlier memory and the computation speed is limited. And if you want to work with these sort of neural networks, and for this neural network, just in a fraction of a second, it trained with already existing data. But in real time for applications, even when I was using this particular neural network tool, almost I need to wait for some 1 or 2 hours to generate one network. With this laptop, whatever I use currently, I need to wait for around minimum of 30 minutes and the maximum of 2 hours for my particular application or the application what I've chosen. But now it is not like that. We have so many sophisticated memory computers we have, and the cost of the memory has greatly come down when compared to that of the earlier days. So I can expand memory to any level. Either I can use it in local memory or I can use the cloud space required for my applications. So I can process GBs of data just like that in the current days. So do you have any queries? You can ask me, or you can post us some question. So I hope I justified you with a very basic requirement. And again, it's an ocean. Not in a day or not in an hour we can complete.